Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the last episode we finished the implementation of image-based lighting for our DirectX 12 renderer. Although there is obviously a ton of features that we can still add to the game engine, its architecture is now developed to the point that it's clear what data we should feed to the engine in order to get a rendered scene. Therefore, I think it's time to integrate the engine into the level editor. This topic will need a few episodes to cover, and in this episode we are going to start moving the shader compilation to the editor side. Before we start though, I'd like to fix two issues that we have in the code for image-based lighting. By the way, I updated all Nugat packages for all projects within the solution. Here we see that a new version of DirectX text library is added. After the update, it moved this block down here for some reason. To update the packages, I just opened the Nugat manager for the solution and updated everything to the latest version. We see here a new package for DirectX shader compiler. Until now, we were using a script to download the shader compiler, because back then, when we started using the compiler, Microsoft didn't offer it as a Nugat package. However, this new Nugat package has been available for some time now, and I'll show you how and where it's used in the solution later in this video. With that out of the way, the first issue that I'd like to fix is a little artifact we get when creating the BRDF lookup texture. As you can see here, it has a bright yellow and a dark spot in the upper left corner. This is where both roughness and n.v term approach 0, which apparently introduces a numeric instability in the shader. In the shader function where we evaluate the BRDF integration, I clamped the minimum value for the alpha term to a small value. This seems to be enough to avoid the numeric instability. Now we can delete the pre-filtering shaders and the default assets in order to trigger shader recompilation and recreation of the lookup texture. Copying the new texture to the content folder of our test project, we can see that the green corner now doesn't have any irregularities. The second issue that I wanted to fix doesn't really have anything to do with IBL, but happens when we render the screen space Skybox. Let me show you the problem by removing the fix and using the old code. So in the last episode we had this line of code that unprojects a pixel position to the world position. It appeared to be working because our scene and therefore the camera are all located around the world's origin. However, moving away from the scene, we see that the skybox starts moving in a strange way. You'd expect that the skybox is rendered at infinity and wouldn't scale when the camera moves, but here we see clearly that it does. And the effect gets worse when the camera's distance to the center of the world is about the same as the far plane of the camera, which we set here to a value of 100 units. The skybox is completely reversed once we pass the far plane. So there are two things at play here. First of all, having a closer look at the onProject function, we can see that it's mathematically incorrect. The problem is that we are doing this perspective divide at the end, but we should really do this right after reversing the projection, which we do here by multiplying with the inverse of the projection matrix. So in case of reversing the view projection and world view projection, we would have to split this into two steps. Do the inverse projection first and then divide by the W component, and finally do the inverse view or inverse world view transformation. The second issue is that the view matrix of the camera contains the translation component, which changes with the camera's position. We should get rid of this component in order to render the skybox as if the camera is always at the center of the world, or alternatively, as if the skybox is always at infinity. So in order to fix this, I split the function into two steps. First, we reverse the projection matrix. Note that I skipped the perspective divide, since it seems to be always 1 for this case. However, depending on the viewport settings, it can have other values, so maybe I'll add it later anyway. Next, we need to apply the inverse view transform. We don't have the inverse of the view matrix, but since the rotation part of the view matrix is orthogonal, its inverse can be trivially calculated by transposing it. This is done by swapping the order of multiplication in the shader code. Here we see that the matrix is applied to a vector. Swapping the order will apply the transpose of the matrix to the vector. We also only take the first 3 rows and columns of the matrix in order to get rid of any translation components, which are in the 4th row or column depending on the matrix orientation. Using this fix, we see that the skybox is now completely static. Now that we know we have an incorrect function in our shader code, we can have a look at the places where it's used. Luckily, the only place where it's used is in the light culling compute shader, and in this case it seems to be working okay as far as I could test. So I'll leave it like this for now. And that's all I wanted to fix. Now we can look at the other changes that I made to the code. In the 3D12 core.cpp, I updated the version symbol that is exported for the Agility SDK to match the new version. Recently, the Agility SDK added a new option for the comparison function, which is comparison none. So I updated this in the helper's header file. Max anisotropy can be 16 for the anisotropic sampler. There is also a new validation error that enforces using a sampler heap whenever this flag is set. However, we are not using dynamic samplers or a sampler heap, so we can't set this flag. Doing so will result in this error that's generated by the debug layer. In the 3D12 light.cpp, I added an assertion. This is in update light buffers function. In the 3D12 shaders.h, I removed the fill color enumeration since we are not using that shader anymore. I also removed the explicit numbering of items. The project file has some changes because we updated the Agility SDK's Nugat package. Now let's have a look at shader compilation. We added shader compilation.h and shader compilation.cpp a while back in the engine test project. I tried to keep the code in these files well organized because I knew I was going to use them in a more official place. And the new home for the shader compilation files is the engine DLL project, which forms an interface between the .NET editor and the C++ engine. We already had the shader type enumeration in renderer.h, so I removed it from here and added the renderer header file instead. I also added a new function for compiling shader code that's already in memory, so it doesn't need to be read from a file. As I'll show you in a minute, we are going to use the shader compiler from a Nugat package, so we don't need to use a relative path for the headers and the compiler library. I also removed all headers that point to the low-level renderer. This will clear the way for using this shader compilation code for other graphics APIs like Vulkan as well. Please do make sure that you are using the headers provided by the Nugat package instead of the ones that come with the Windows SDK. Since we are not including the headers for the low-level renderer, I duplicated this macro for when we call functions of the compiler interfaces, which return an hresult error code. I also duplicated this engine shader enumeration since it was defined in d3d12 shader.h. And here the fill color shader is removed as well. By the way, I'll show you the entire code in this file as it is later, but I'll first explain the changes. Here I added a new buffer that will hold the error messages that can occur during compilation, and I renamed this assembly to assembly. Then I added a new function that uses the shader code in the memory for compilation. This is a new function that takes a pointer to the source code, the length of the source code, the type and function name of the shader, and a list of extra compilation parameters if any. We copy the code to a buffer that can be used by the shader compiler using the IDXC blob encoding interface. We set the function name and the shader type in shader file info and call an already existing compile function to do the actual compilation. It's this function which takes the source blob and the list of compiler options, which we've been already using for compiling our shaders. As you can see, it hasn't been changed, except now it also returns any errors that might have occurred. The getArgs function simply assembles a list of compiler options. It didn't change much, except for the fact that the file name is made optional, since we want to also compile shader code that's already in memory. Here we were using d3d12 shader bytecode struct, and since we have no longer access to d3d12 specific API, I just used two local variables for the bytecode pointer and the bytecode size. It looks a bit messy, so let me show you the actual code. Here's the function that saves the compiled built-in shaders to a file. Next, I added a new function, which was already there partially, but I factored it out and made it so that we can optionally also include error messages and the shader assembly. This is because when we compile a shader and send it to the engine for upload to the GPU, we don't want to include the assembly information, and obviously we don't have any errors to begin with. This extra information is used when we are writing or constructing material shaders in the editor. The data will be packed in this format, where, as I mentioned, the error and assembly blocks are optional. If we have valid bytecode, we can calculate the total buffer size that is needed to pack this data. Here we see that the extra buffer size is 0 if we don't want to return the extra data. Then we allocate this block and use blob stream writer to write the data. We write the bytecode size, followed by the hash code and the bytecode. If we want to also return errors and the assembly code, we write the size and content of those as well. We might want to add an assertion or check to make sure that these pointers are valid, which I forgot to do. At the end, we return the buffer. The two shader compilation functions simply use the shader compiler class to compile the shader and call the packing function to create a buffer that contains the shader data. And the last function is for compiling the built-in shaders, which is the same as before. Now I'll show the whole file again, so you can pause and make sure that you have all the updates as well. As we saw before, we have a new function in the shader compilation header file. We can call it in one of the engine API functions, which in turn is called by the editor. We'll look at this in the next video. Before we go out, I'd like to say a huge thank you to all of you who are supporting this channel on Patreon and Ko-fi, and a very special big shout out to our new tribal elder Justin. Thank you so much for your very generous support. As always, thanks everyone for watching, and I'll see you next time.